So, good morning to all. I am Ashok Putate. Today, I am going to conduct the lecture on digital design and hardware description language, that is the HDL. So, in that, the previous lectures we have conducted the points. These points are the sequential statements. So right now, after that sequential statements, we have studied the case statements, procedures, or the statements. After the module number second, we have started, and in that module number second, we are studied about that hub adder and the full adder. So in that hub adder, we know that we are adding that 2 bits, and in that full adder we are adding the 3 bits. So after this hub adder and full adder, we know that how we are able to design a code for this hub adder with its truth table. So here firstly we are define the entity and architecture, and we are calling the libraries. So in sometimes here the libraries are not written, but we have to write down the libraries, or that library declaration we have already known, or we are using the IEEE library. So in that, firstly we define the entity, or this entity is, or in the previous one we have given to name to that entity, or here the hub adder. So in that entity, what we are defining? We are defining the input and output ports of our digital circuit. So in that digital circuit, we are using the hub adder. In that hub adder, the input ports are nothing but the A and B. The A and the B are the input ports. So here hub adder, the A and B, these 2 bits are acting as the input bits, and here sum and carry acting as the output bits, or here we are calling this one as a ports. So here A is nothing but in STD logic, or here input standard logic. Then B is also input standard logic. That 2 logics we are defining. Then here, so the output is nothing but the first one is the sum, or here the entity we are defining that hub adder as a HA, small h, small a. That is the name of this entity, or we are calling this one as a hub adder. So here the sum of hub adder is given as S, that is the S is nothing but the output. So instead of that simple S, we are writing as a SHA, and in that one, this one is nothing but the out STD logic, or out standard logic. Then in the similar way, the next bit is the carry, that is the carry, or CSHA, that is the out STD logic, and we are ending that hub adder, that is the ending of that hub adder input output port declaration. The next one is nothing but the architecture, or how that architecture is functioning we have to define. So defining that architecture, we are giving the name to that architecture as a behavioral. Behavioral is nothing but the hub adder, or here the name of that architecture is the behavioral op, and after that, after this of, there is a presence of the entity, or entity name is hub adder. So here the architecture behavioral of hub adder is. The next one is nothing but the begin, or here we are starting the process how that can be executed. So in that execution, here behavioral begin, then sum, or sum assigned the value of, or that sum is nothing but the, from this get structure, the sum is nothing but the, that get is nothing but XOR get A XOR B, that's value is sum. So here the sum assigned value of A XOR B simply. Then here the carry, or to define that carry we are using the AND gate. So how can we define AND gate? Or here AND gate is nothing but the product of the 2 input bits, or A and B, or in that mathematical declaration A dot B. That is nothing but the AND operation. A dot B is equal to C. So in the same way, in that description of this hub adder, we are writing as a carry of hub adder is assigned to a value of that uh, less than or greater than sign is equal to, that is we are calling this one as assignment sign. So that carry is assigned to a value of A and B and end of this behavior. So here by giving the values to that A and B, we are obtaining the output, or here the input like A and B values, we are able to obtain the output. So it is a very simple language. We are describing that hardware structure. So the next part is nothing but about that full adder, or full adder is difficult to implement than the half adder, because here in that full adder we are using a different gates we are using, or in that half adder simply the two gates we are using, but in that full adder the number of gate required are more. So here the two XOR gate, two AND gate and one OR gate we are using, or here approximately 1 2 3 4 5. By using that 5 gates we are defining, or here the operation of that sum is nothing but equal to A XOR B. Then after that, that ax or b's value is here. After this ax or b value is ax or b value bracket with x or c in is nothing but our sum. So here to define that value, how we are able to write the HDL code. So the difference between hub adder and a full adder is that the full adder has three inputs and two outputs. So here it is difference is that three inputs are there and same the two outputs are as it is previous one. So whereas in that hub adder only two inputs and two outputs. So the first two inputs A and B are, the third input is an input of carry in, or that is nothing but the carry in. So when a full adder is logic, or full adder logic is designed, you string 8 of them together to create a byte wide adder. 8 bits addition we are able to perform and cascade the carry bit from one bit adder to the next. So here in that diagrammatical form, in the black box form, we are giving the adder as, so the inputs are nothing but the A, B carry in, A, B and carry in. These are the three bits. A, B and carry in. These are the three bits, and in the output side, the two bits are, the two ports are present. So first port we are calling this one as the sum, and the next port we are calling this one as the carry out. So here the carry out is designed as C out, and the normal output is designed as S. So here sum is designed as the S and carry is designed as the C out. So the next one, the full adder truth table, or how we are able to obtain the truth table of this full adder. So the output yes is an XOR, or we know that output yes is an XOR between the input A and the hop adder. The next one, the sum. Sum is nothing but output with B and C in as a inputs. So here the sum is output with respect to B and C in. Take C out will only be the true if the two inputs out of three are high. Out of three are high. So take carry out. Carry out when the carry out is present or is available when the two inputs out of the three, or here we are having the three inputs A, B and C. If above or in that three inputs any two inputs are high, at that time the carry out is also high value. Or if there is 1 is present or available in that A is 1, B is 1, the value of that carry is also 1. Or A is 1 or C is 1, A and C are 1, then here carry is also 1. So the truth table of that full adder, it is having the inputs A, B, C, I out, or here inputs and outputs. So input pins are A, B and C, and output pins are nothing but the C out, S, C out, C in, that is the carry over. Here A, B, C and carry out, and this S stands for the sum. So if there is 0, 0, 0, if that 3 bits are 0, at that time carry is also 0, sum is also 0. If there uh, 3 bits 0, 0, 1, or here carry is 1, at that time the carry out is also 0 but sum is 1. Or if we are considering any 2 bits are 1, or here any 2 bits are 1, at that time the carry bit is 1. So here 1, 1, then at that time carry is also 1, but here 0, 1, 1, sum is equal to 0. So these are nothing but the output. So to design that full adder circuit, we can implement full adder circuit with the help of the two hop adders. So by using two hop adders, we are implement a full adder circuit, or interconnecting the two hop adders with each other, we can easily able to obtain the hop adder circuit. So here first hop adder will be used to add A and B to produce a partial sum. A second hop adder logic can be used to add C in to the sum produced by the first hop adder to get the final S output. So here full adder logic circuit. If any of the hop adder logic produces a carry, there will be an carry out. If out of that two, anyone produces a carry, the output is also carry. A C out or carry out will be an OR function of the hop adder carry out. So here OR function, you know that 1 or 0 output is also 1, or 0 or 1 output is also 1, or 1, 1. So that first statement can be obtained by using the OR function. Then the implementation of larger logic diagrams is possible with the full adder logic. A simpler semantic representation of a 1-bit full adder is shown in figure below. So here we are simple in the form of the gates, XOR gate to XOR gate to AND gate and one OR gate. Or we also remembers that in that full adder how many number of XOR gates are available, how many number of OR gates are available, how many number of AND gates are available. So in that full adder circuit, 2 XOR gates we are using, 2 AND gates we are using, and 1 OR gate we are using to implement the sum and carry out. So by using that two hop adder circuit, in that two hop adder circuit, the first one P and Q, or instead of that A and B, here we have written as P and Q. The P and Q, then hop adder output. Hop adder output, in that hop adder output, there is a sum and one is carry out, or we are providing that carry out to the OR gate. Or previously we have known that that function or cout will be an OR function of the hop adder carry outputs, or that two hop adders carry output is nothing but carry output. That is first carry output, second carry output. They are OR function, and that is nothing but our final carry output. So, and in that half adder, the sum of that two parts is added with that sum of next pin. So here the 3 bits we are adding S, or here we are known as a carry in P and Q, and based on that 3 pins we are obtaining the sum. So with this type of symbol we can add 2 bits together, taking a carry from the next lower order of the magnitude and sending a carry to the next higher order of the magnitude. So here the carry we are taking from this first adder, so here second adder, and from this we are giving to the higher value or output values. So full adder table, or in a computer for a multi-bit operation, each bit must be represented by a full adder and must be added simultaneously. To add two 8-bit numbers, you will need 8 full adders. Always remember that to add the 8-bit to 8 bits, or here there are 1 to 6 or 0 to 7, and here next 0 to 7, or these two 8 bits. When we want to add at a time, we need 8 full adders, which can be formed by cascading 2 of the 4-bit blocks, or here by cascading of these blocks one after another, we are able to obtain the sum and carry out. The combinational circuit combines the different gates in the circuit, or here we know that combinational circuits are made up of the gates, and sequential circuits are made up of the flip-flops. So the examples are of this full adder are nothing but the encoder, decoder, multiplexer, demultiplexer. In this one, the addition operation is performing in that decoding, multiplexing, encoding, and demultiplexing. So full adder truth table, the output at any instant of time depends only on the levels present at their inputs. It does not use any memory. The previous state of the input does not have, or here we are using generally normally a gates in that to design that circuit. Due to that gates doesn't require some memory for the storing purpose. But here we know that the flip-flop is a 1-bit memory. The flip-flop stores the data, but gates does not store the data. So it does not use any memory. The previous state of the input does not have any impact on the present state of the circuit. It can have a number of inputs, or here that full adder, or here if we are designing the adder circuits at a time, it can have a m number of inputs and m number of outputs, or carry out somehow we can able to obtain. So to relationship between that full adder and hop adder. So here hop adder produces results. The full adder uses hop adder to produce some other result. Similarly, full adder is of 2 hop adders. So here the similarity between that full adder and hop adder. So hop adder and full adder are both produces the result, or that result is the addition of the input. Similarly, that full adder is also having a hop adder, and hop adder is also having a hop adder. The full adder is the actual block that we use to create an arithmetic circuits. So to create that arithmetic circuits, we are using the full adder circuit. So design that full adder through the circuit, or here we know that in that diagram we are having the 3 bits as input. So first, when we are writing the statements in that HDL code, firstly we write the library. After that library, the entity description, or entity, we are calling this one as a name of that entity, or here generally we are calling this name as a full adder. So the inputs are 3 inputs P, Q, and carry in. So in that entity, we are describing the input output pins. So here the port A is nothing but the in STD logic, B is also in STD logic, C, I, N is also in STD logic. Then the output bits are 2 bits or uh, two pins. These are having the outputs. The output is at sum and output is at C out, or sum is out STD logic. Count C out is also out STD logic. So in that way we are defining the entity for that full adder circuit. So there is a small difference is that C and C in. That C in is extra bit added into our circuit. So if we check the programs, or here the entity F adder is entity F adder is. So here the pins are A, B. These are 2 pins, but in that our full adder designing, we are using the 3 bits. So that 3 bits are nothing but the A, B and C, I, N. A, B and C, I, N. That 3 bits we are using. So the 3 bits, and the output is given as sum and C out in the same way, out STD underscore logic or standard logic, out standard logic. The next one, the architecture, or how we are describing the architecture of this full adder. For the describing the architecture of the full adder, the component of this hub adder, or here the architecture is defined as behavioral of full adder. That is the name of this architecture, and is component hub adder, because here the entity we have given the name or here architecture, the behavioral is name of this architecture, and full adder, full underscore add is the name of the entity. Here entity name is full underscore add is the name of the entity. Then in that one, we are defining that full adder circuit by using a 2 hub adder circuits. So in that component of hub adder or hub adder circuit, or here in the previous one, we have defined the hub adder. So here the defining of that hub adder we are calling in that full adder circuit, because the full adder circuit is made up of the 2 hub adder circuit. So here component hub adder is port A in STD logic, port B in STD logic, SHA out STD logic, carry carry out of this hub adder, that is out STD logic and component. Similar one in the previous one hub adder we have defined, we have to write down that same statement, component of hub adder. So here in that component of hub adder we are defining that hub adder. Then next one, the signals, or which signals we are using, that is the S to S, C1, C2, that is the in STD logic signals, or the logical signals which we are using in that is S underscore S, comma carry 1, then carry 2, that is the STD logic signals. So here begin, the next one we are processing that output statements of this full adder. So here that begin hub adder A1 or HA1 is nothing but hub adder, because we are forming, or we are defining that circuit from these 2 hub adders. That is the first hub adder, or here that is the first hub adder and the second hub adder. By combining that 2 hub adders and with OR gate, we are defining the sum and the carry out. So to define that, the begin, then hub adder, Then HA port map, or here port mapping, we are using the A comma B comma S underscore S, that is a one signal. Then here C1, that is the clock 1 is another signal. Then hub adder 2, or in that hub adder 2, so by using that hub adder 2, so in that hub adder 2, so in that hub adder 2, the same as previous one, that is the hub adder port map S underscore S comma C in comma sum comma C2, or carry output of that hub adder 2, carry output of that hub adder 1. Carry output of that hub adder 1. Then C out, or we are defining the carry out is nothing but the ORing operation of that C1 and C2, or ORing operation of the C1 and C2. So which are the C1? C1 is from this hub adder first C1 and hub adder second the C1, that is the C1 and C1, and when these both are ORed with each other, we obtain the carry out. Then end behavior, end behavior. So in that way we are defining that hub adder and full adder structure. So if there is any doubts in that hub adder and full adder structure?
No.
No. Okay. Then the next point which we have to discuss, subtractor and the multiplexer. So here subtractor, or their VHDL codes for this subtractor. So we will wait for some time. So in the next one is nothing but the hub subtractor and the full subtractor. Similar previous one, hub adder and full adder. The hub subtractor and full subtractor are also the combinational logic circuits that are used to subtract two 1-bit numbers. And or here in that hub subtractor for the two 1-bit numbers, full subtractor for the three 1-bit numbers. They both produce two outputs, difference and borrow. So here in that adder circuit, there is the output is in the form of sum and carry, but in that subtractor circuit, the output is in the form of uh, difference and the borrow. The hub subtractor does not account for any borrow, or in that hub subtractor there is no any borrow is present, only subtraction part or difference part is present. So in that full subtractor, in contrast, has the three inputs, one of which is borrow input, or here in the inputs the A, B and borrow in, that input is present. Since the full subtractor considers the borrow operation, it is known as the full subtractor. Because here the borrow operation is present, due to that we are calling this one as the borrow subtractor. So in that hub subtractor, the diagram for this hub subtractor is as like, or we are implementing that diagram by using the logics. Or in that one, if the input is A, the input is, so here A and B, these are the two inputs, and here the difference and borrow. If the value of this A is our first bit, B is the second bit, or if A is 1, B is 1 at a time, 1 minus 1, the output is 0, and the borrow is 0. But if A is 1 or A is 0 and B is 1 at a time, the difference is the difference is the difference is 0 and borrow is also 1, because here the value of that A is less than value of B. So that gate is nothing but the XOR gate. So this gate is the NOT gate, and the third gate is the AND gate, or by using that three gates we are obtaining the output for this. Or here the difference is A X or B, and borrow is A dash B. So to obtain that VHDL explanation for this code, or here the firstly we are describing the library declaration, or in that library declaration, so that library declaration is nothing but the library IEEE, use IEEE underscore std logic underscore 1164 dot all. That two statements we are able to write, but we can also write extra, that is the use IEEE std or standard logic arithmetic all. They here ARTH is nothing but the arithmetic declarations that we can also use. Then here logic unsigned, here the logic unsigned, because signed and unsigned, that two declarations are present, that unsigned declaration which we are using. So for that, after that creating that library functions, then we create an entity. Firstly, the library present, library functions or the statements regarding the library. Then second one is the statements regarding the entity. So here we define the input and the output ports of the design. So entity, in that entity we define the input and output ports of the design. Here we have two input bits, A and B, or in that diagram A and B, these are the two input bits, and at the output side difference and borrow. At the output side we are defining as the DIFF. DIFF is the difference, and the second bit is the borrow. And don't forget to end the entity as well. When we are writing at the time end entity, or here the declaration starts at the time where we have to write end of this part. So entity hub adder, the name of that entity is nothing but the hub subtractor. Entity name is hub subtractor is. The next part is port A comma B. A comma B, these are nothing but the in yesterday logic, or here sometimes we can able to write that A assigns the value of in yesterday logic, B assigns the value of in yesterday logic. That two separate statements we are able to write, or instead of that, if we give one comma in between that A and B, that two statements we are able to combinedly write. Then next one, these are the two are nothing but the input standard logic bits. Then output standard logic bits are difference and borrow. These are the out std logic and end of this entity. Or in the previous program we have seen that that program is written in the capital letter form, but here the we have not any we can small letters, we can also write this program. So here that is the case independent VHDL coding, or here the VHDL coding is a case independent, whether we are writing in the capital or in the small form. Then we start writing the architecture. Here the input output declaration we have given. After that, the architecture of behavioral, how that function can be work for this hub subtractor. Here remembers that in that hub subtractor only difference and borrow are available. So in that architecture design flow, or that the architecture name is given as. So here we have given the entity name. Entity name is hub substructure. So here architecture name is data flow of hub substructure, or here the data flow of entity. So how that entity can be works is begin DIFF or difference. Difference is nothing but the A, X or B. Difference is A, X or B, and borrow is uh, not A and B. Not A and B. So here how the difference is present, or in that X or operation, if both are present or both are similar, if both the values are same in that, or here the output of that XOR gate, remember that in that XOR gate, when the both values are same, the output is high. And if that both values are different at the time output, or here the in that XOR operation, so similarly for this borrow is nothing but when there is subtraction, or here A value is greater and B value is less. We are subtracting A from, or here A minus B. So here not A, or if there is a value of A is 1 and B is 0, at that time the difference is 1. And if not A means if here is 1, here it is a 0, 0 and 0, the borrow is 0. 1 minus 0, value is 1 and borrow is 0. But here if that value of A is 0 and B is 1, what happens? A is 1 and B is 0. A is 0 and B is 1. What happens? Give answer. A is, or in that difference, if A is 0 and B is 1, 0 minus 1, the 0 minus 1 difference is 1, but borrow, because here 0 minus 1, the borrow is something that is here the value of A is 0, not A means the value is 1, and here B value is also 1, 1 and 1, 1 and 1, borrow is 1. So we are ending that architecture. So also remember to choose the architecture using AND keyword, or we are writing that architecture as an AND keyword. That is, we are always writing. Then for this full substructor, or in that full substructor, we are using the entity declaration, library declaration is same. For this hub adder, this is also same. For this full adder, this is also same. Use IEEE.std underscore logic 1164.org. Then here entity hub adder, here up substructor is, the entity name is hub underscore substructor, same here entity name is hub underscore substructor is, that statement is same. Or here the port A comma B, but in that full substructor the 3 ports are present. So here the ports are nothing but the A comma B in STD logic, then difference and borrow out STD. Here the A and B, these are nothing but the in STD logic, and difference and borrow are the out STD logic. But here the signals, we are giving the signals as A, then B, then difference and borrow. That signals are the standard logic signals. And for to create that code, we are writing in the process form, or here in that process form we starts with the begin, then UUT, that is the UUT, that is the hub substructor port map, or how that port mapping can be done. So A is assigned value of A, B is assigned value of B, and DIFF is assigned the value of the difference, because here the two parts are there. The difference is also present in the output side. Here the output is, we are obtaining the difference. These are the output, but that difference we are applying as the input into that full subtractor circuit. So borrow is assigned value of borrow. So here signal or stigma in process, or in that stigma in process we have starts with the begin. If A is 0 and B is 0, wait for the 20 nanoseconds. We are giving the wait signal is here for 20 nanoseconds. If the A assigned value of 0, B assigned value of 1, we have assigned wait for the 20 nanoseconds. If A assigned value of 1, B assigned value of 0, we are waiting for the same way for 0 0 0 1 1 0 1 1. So here separately we are writing and wait and end process and end TB. So here firstly when that A is assigned a value of 0, B is assigned a value of 0. So here A is assigned a value of 0, B is assigned a value of 0, then the difference is 0 minus 0 is equal to 0. And here the borrow, so here A is not less than or greater than B, so here borrow is also the 0. So here one by one process we are executing. Or here register transfer logic level semantic of this hub subtractor. In that hub subtractor, here AND gate, but here we are not A, because the output of that AND gate is, so here we have defined the code for this hub subtractor. This hub subtractor, the output is DIFF. DIFF is value is nothing but the A XOR B, and borrow value is nothing but the not A and B. So that AND gate is giving the borrow value. So that AND gate giving the value of the borrow value. So here not A and B is equal to borrow, and here the A XOR B, the value is nothing but the difference. That is the hub subtractor. And this one is for the full subtractor diagrams. In that full subtractor diagrams, the 6 gates are used. First one is the XOR gate, which can be used for giving the difference. Here the bits are A, B and D as the input bits we are using. Then here how to find the borrow, or in that borrow not A, then here then not A is given. Then from these two gates, that is the OR gate and here the AND gate, ORing of B and D and ANDing of B and D. From this one ORing operation that is applied to the OR gate, AND gate actually, this one is the AND gate, then here from this AND gate to the OR gate. So we can see that the difference is nothing but the A, or here the difference is nothing but the A XOR. To write down that XOR symbol, we firstly write addition, then circle around that addition. That is nothing but the XOR operation. XOR operation A XOR B XOR D. That is the three inputs. Then borrow, to find out that borrow. So here firstly A naught is there, that is the A dash. The dash is nothing but the A naught or not A operation. Then into bracket B plus D, or here that part is nothing but the B plus D. That is the multiplied, because at AND gate that part is multiplied with that OR operation. So here A naught into bracket b plus d plus, here the or operation plus, that output is added with that b dot d. The output is added with the b dot d. The total output is added with the b dot d. From that we are generating the borrow output. So by using that data flow method, we are also able to explain this one. So here in that entity is same, standard logic IEEE declaration is also same, that two parts are also same, but here the structure or architecture, so here full subtractor is difference, or difference assigns the value of a, x or b into bracket x or c. That is, by using a single line we can able to obtain the difference. Then to write down that borrow it into a double bracket here, not a bracket close, and b or c, or that mathematical expressions we are writing, or here not a, b plus d means b or d, and B and C. So here generally we are using as A, B, C as the inputs. Here the A, B, C inputs we are using, but here in our previous one we are using the inputs as A, B and D. Here A, B and D, these inputs we are using. So instead of that, if their value is A, B and C, if A, B and C, so here the output difference is nothing but A, X or B, X or C. And in the same way, so here not A uh, and not A bracket, in bracket, here what happens, B or B plus C, instead of that D, if we write C, here B plus C, that is multiplied, and that sum is added with the part of the B dot C. That part is added with the B dot C. So for this one, we are using the ABC as in STD logic. So here not A and B or C bracket close, or B and C. So end of this data flow. So here a different way we are able to write down the VHDL code for the subtractor. So here by using the test benches, we are also able to write that code. Then RTL schematic for this subtractor. For this subtractor, the RTL schematic is like A, B and C. The XOR operation, or here the output is nothing but the difference. Difference is nothing but the, here the value is A is given to that first gate, then the second, the value is B is given. So here that A X or B, then also that is added with the value input value. So this one is the C, means here A X or B, X or C, that is the difference, A X or B, X or C. Then in the borrow side, for this borrow side, we are using the not A, or here the upper side, the not A dot, here B or C, or B plus C multiplied with not A, and that part, or here or get means addition, that part is added with the B dot C, B dot C. We are adding that part, so we obtain the borrow output. So these are the simulation waveforms. There is full subtractor A, full subtractor B, full subtractor C. That is, these are the three inputs A, B, and C, and difference and borrow. Remember, if that value is upper heighted value, that time this value is 1, and if that value is lower, that value is 0. When here the value of A, or that two parts, or here the positive half cycle, negative half cycle, or like that half cycle we are moving. So for this half cycle, that value is 0, next half cycle this value is 0, or here A is 0, B is 0, and C is 0. If that three values are 0, then here difference is also 0, borrow is also 0. But here if that A is 0, B is 0, but the C is 1, or 0, 0, 1, or we know that B minus C operation. So this gives the difference as a 1 and borrow as a 1. So in the similarly, if A is 0, B is 1, C is 0, or here 0 minus 1 means here there the difference is 1 and borrow is also 1. Then here if that A is 0, B is 1 and C is 1. So here 0 minus 1 minus 1. What happens? The difference of 0 minus 1 means here the, or here 0, then minus 1, and here minus 1, minus 1, minus 1, this also 0, or 1 minus 1, and but here the borrow is also 1 because 0 minus 1 we are operating. Then here if A is 1, B is 0, C is 0. If A is 1, B is 0, C is 0, then 1, and difference is 1 because 1 minus 0 minus 0, that is also 1, but here the borrow is 0. So here 1 minus 0, 1 minus 0 and minus 1, or here 1 minus 1, the difference is 0, borrow is also 0. In the similar way, we are see that waveforms. So we will conclude our today's lecture. In the next lecture, we start with the multiplexer, or how we are able to write down the code for the multiplexer. So any doubts regarding that points, half adder, full adder, half subtractor, full subtractor?
No doubt.
Okay, thank you. We will conclude our lecture.